Okay, guys, hello. Today we're going to go over the series Converge or Diverge um, using the integral test. All right, first, let's learn a little bit more about where the integral test came from. This man right here, Augustine Louis Cauchy, was the known creator of the integral test, also known as the Maclaurin-Cauchy test. He was very influential in the 19th century, and he did a lot for calc and algebra and also number theory. Okay, before we get into the series test of the integral, using the integral test, we have to understand that there needs to be um, you have to have an organized way of thinking of these tests, and you need to know how to go from one test to the next test to the next test in a quick, easy way. So me and my group, we put together this game plan, this link right here, and it would show you um, how you can think about these tests and the steps you need to make in order to find the right test for your series. Okay, now let's get into the integral test. What is it? Okay, basically, like we said in the beginning, it is a way to tell if a series converge or diverge. But the series have to have the following conditions. It has to be continuous, meaning there's no breaks, no jumps, none of that. You should be able to take your pencil, follow the graph, and not have to lift it one moment, okay? It has to be positive. There are multiple ways to find out if it's positive. Um, But basically, you just want to make sure that throughout the whole graph or like the series, it's staying positive. And it has to also be decreasing. And you can find out if it's decreasing by taking the derivative. And if the derivative is negative, then it's decreasing. Now let's get into the integral test. If a related function f applies and complies to all of the conditions that we had listed in the previous slide, then we may use improper integral to figure out if it's converging or diverging. If the improper integral is diverging, then so is the series. But if it's converging, then the series is also converging. Okay, how to use the integral test. Okay, here I'm going to go over 3 examples for us, a diverging, a converging, and an inconclusive example. First one right here is diverging. We have the series 2 over 5n minus 1, and since it checks off the list, we know that it is continuous from 1 to infinity, and it is um, decreasing, and it is positive, we will now use the integral test. So here is the details of the integral test. We take the limit of b going approaching infinity, so on and so on. We evaluate the integral, and in this situation, we got infinity. And if anybody remembers from the integral test that if you get an infinite number, then the integral diverges. So in this situation, so should the series. Okay, here is example 2. This is a converging series. We have the series right here, and we follow the steps. We first make sure that it follows the conditions. We're going to take the improper integral of it, and then we're going to see where the improper integral takes us. We got a finite number. So, as we remember from integral test, I'm saying nothing. Sorry. I remember from improper integrals. We know that when we get a finite number, it converges, so should the series. So here we have an inclusive example, okay? We have the series 8 cosine of pi n divided by the square root of n. Okay, so we already see that there are problems. One is not decreasing. Like it's not continuously decreasing. It's going increasing, decreasing, increasing, decreasing. So it's also going from negative, positive, which means that it's not positive, and that that doesn't go with two of our conditions. So what do? We just use another test. We're going to simplify cosine of I n to -1 over n. And now this looks a little familiar, right? This is the alternating harmonic series. So we have an alternating harmonic series. What test should we use? Maybe the alternating series test. And the condition for that is 1 over n has to be decreasing. Check. The limit as n approaches infinity is 0. Check. And it's alternating. Check. So, since all of the conditions are met, the series converges by the alternating series test, but not by the integral test, which is totally fine because we have other tests to use. Now we've come to the end. We have seen 3 examples of converging, diverging, and inconclusive results from using the integral test. And now let's conclude everything we learned and everything we just went over. First, make a related function. Solve, take the improper integral of the related function, find out if the integral converges or diverges or is inconclusive, what the integral does, so should the series, and if all fails and you can't use the integral test, just use another one. Follow your game plan and don't panic. Take your time. Practice a lot. Thank you for sitting here with me and going over the integral test with me. I hope you guys learned a lot. And I hope you guys enjoyed it because I enjoyed making this.